I just think it's important to go over some of the aspects of Bohr's work and how I think it's misrepresented in the textbooks. Niels Bohr did a very important job of explaining how we can get line spectra from the atoms, how the energy levels of the hydrogen atom are represented, and so on. Unfortunately, I think perhaps for simplistic reasons, who knows why exactly, this gets in the textbook, and I think it gets in the textbook in a way that is incorrect. And I don't believe we should be teaching children things that are wrong. I think we can say to them, okay, this is where we're starting and it goes here, but I think we should be very cautious about teaching things, even if that is convenient, for the age. I think if the children can't manage something, then we'll wait a year and teach them again. So this is things that kind of bother me. So I thought I'd make a short video about this. So this covers things like Bohr-Rutherford diagrams. It also covers things that Bohr's work implied a little bit.
As young people learn the topic of quantum mechanics or just even getting introduced to the atom, often we use a lot of models that we think young people already understand and try to extrapolate from that. One of the challenges I think we have in this particular case is that we're modeling things at the atomic level, which is not a macroscopic world. It is a quantum world with a completely different set of rules. And I think that if we're not careful when we do that, I think we mislead our young people. And I think the problem is that the first time you instruct students in these concepts, and you do it in a very straightforward way, it's something that sticks. And it's very hard, I think, later on to move that away, even if that child is pursuing that type of study. You see the equations and the complexity of what's really going on, but it's so easy for your brain to go back to this other version that you were familiar with as a child, even if it's wrong. So I think we want to be careful in this whole thing about what we say and what we don't say to young people about certain things. Obviously, whatever we introduce a new topic in any subject, we're not going to cover the whole thing to the extent of human knowledge at any given time. But there is a reason, for example, let's say that the subject of physics is not meaningfully engaged until grade 11. There is a reason that we have children starting to read at the age of 6 or 7, and all the rest. We choose ages where we think it's a reasonable time, for the majority of them at least, to be able to begin to understand these comparatively abstract ideas. And remember that in the case of atomic physics, no one has seen these things. This is all magic. The children have to accept what you say. They don't have a daily experience with electrons and protons that they can perceive. So they basically have to be told this material and in effect do what they're told. And so as a consequence, there's a challenge here about trying to be correct about it. Now here in this image you see a typical solar system model. Now this, of course, in its own right is flawed because the planets are vastly more separated than this would suggest. But given the space and size of the planets, we recognize these things have to happen sometimes. And we move naturally from that to this model of a hydrogen atom where you have an electron going around in a spherical circular orbit around a single proton. And this is something that is very similar to a planetary model. It's easy for young people to grasp. And very quickly we move from that then to what is typically called in the schools the Bohr-Rutherford diagram. And now we have this, it looks like a carousel at a county fair, electrons going around in this manner. And this is where I think we make a significant mistake in allowing this type of thing to be taught to children, because it has absolutely nothing to do really with how an atom is structured. The next thing that happens for many young people is that they encounter Hollywoodizations of atomic images, and of course the images in the media and in the cinema are very powerful. And so we get again, now this atom here certainly does show a three-dimensional view, which is encouraging. but there's still a lot of symmetry here, and there's the issue of multiple electrons and so on, and it is still very representative. So here we are back, if you will, kind of the way that Bohr had envisioned things initially. And I think we need to say a few things here before we go further. The first thing we have to remember is, well, before I do this, in this particular diagram, just so you're clear, that V that you see is not actually a V. It's a Greek letter called nu, which stands for frequency. So you may have seen Planck's equation before as E equals hf. So this is E equals h nu, which means exactly the same thing. So please don't fret. But here's the main point. The Bohr radii, the Bohr orbits that you have, which should not be thought of really as orbits. They should be thought of as energy levels in the abstract. And so when you're moving from one energy level to another, if you come down an energy level, you emit a photon. If you move up one, you have to absorb one. You need, of course, energy to move up. So that makes perfect sense. And so there's, I think we need to really remember that. And when we look at Bohr's work and we look at any model of the atom, we got to get away from the geometry thing at this level, and try to think of it more in the abstract, that we're dealing with energy, and we're dealing with energy moving around the particles, if you will, changing their energy circumstances. And the point is that that energy can be changed only in a very specific way. It cannot be changed in some in-between amount, which is, of course, the classical world, but it is a very defined amount. It has this energy, and it will go to that energy, and there's nothing in between. And if it absorbs, if a photon comes in that doesn't fit that, then it won't absorb it. So I think we need to really make sure that when we work with young people with the Bohr atom, and I don't mean this merry-go-round of atoms, but just the energy level idea, we're very, very specific that these circular pathways, if you will, are not really the path of the electron in per se, but rather a construct to think of its energy level, its energy at that time. Now, of course, we can calculate those in electron volts, but that's not really, helpful to us. So the diagram does make things a bit more clear, as long as we're not careful to extrapolate too much from it. In his work, Carl Sommerfeld, of course, showed that ellipses do work as well, and he had this scheme to show that at higher energy levels there are a whole bunch of subtypes that show up that give us these micro levels that lie in between. Now, when I spoke about the elliptical aspect of this in my previous video, I was referring to something a little bit different, that's sort of a little bit more along my own thinking on this. So if you have an electron orbiting the nucleus, if we think about it more or less a little bit in the classical sense, the way Bohr was thinking about it originally, and he shows the circular path because the math's really easy, that's fine. And he's still quantizing the energy. He's still saying the amount of energy that that electron has in that particular path is whatever, it's a certain amount. And so if we move from circles to ellipses, we still have to maintain that energy level. We cannot play with it if we're going to maintain, where we are. And so what I'm suggesting is that the pathway could be different and still maintain the same energy level. And this would lead to a less clear sense of where the electron actually is. And I don't think that it immediately violates the concept that Bohr was talking about, because once again, if we don't think of Bohr's work as straight radii and geometric concept, but rather more as an energy concept, then whether the path is elliptical or whether the path is circular isn't important anymore. It is the energy that is important, that makes the difference about this particular electron. And so and I also wonder if an electron was absorbs a photon, at a particular point. And we know, for example, from the photoelectric effect, that such an activity is going to impart momentum. It seems reasonable to me this would change the shape of its path, and that to retain a circular path seems hard for me to accept. So I know I'm departing a little bit here from established theory, but I just feel that it's something to think about. And so Sommerfeld's idea here was to look at higher levels of energy, and that you have suborbital types, and this is his version of it. I'm stealing the diagrams a little bit to show you that in this particular case, with this diagram drawn as it is, the semi-major axis of all these orbits is exactly the same. And so if that's true, and it is geometrically speaking, and we have everything else, we have a proton and we have an electron, of course. The proton's a small black dot in the center, and the electron is, of course, following one of these paths, and every other conceivable one in between that would still fit within that energy. Okay, so there's a limit. You can't go beyond a certain distance away, so there's going to be a constraint. But there would be then a distribution within this that stays within the energy that is required, and this would allow for us to sense. And when you look later on at, say, models of the s orbitals, for example, solved with much more difficult equations than anything we're talking about here, you do get a density plot, and you do get a sense of where the electron is more probable than where it's less probable. And the idea of an orbital being that the electron is this is a probability zone of where you might find it, shall we say. So I just feel there's still something to be said for this, and if nothing else, I think it's a way to introduce this concept to young people, hopefully not crossing too many lines. Here we have a quantum a microscopic view of an atom, whatever that exactly means in the sense of what we're looking at here. This will be on false color, of course, to show you what things are. But we'll draw our attention to a couple things just to give you an overview here. The reddish and yellow area in the center would be the nucleus. Notice that that is not a point, that the object in the nucleus is moving around. It's not staying put because of the uncertainty principle. It must do so. And then you notice the bluish, the lighter blue area outside of that, which is the location of where the electron can be. And what you'll notice here is a couple of things. And I'm guessing a little bit from this, but I think I'm probably right. The denser circle you see in the middle, that's almost filled in, is the first shell, the first S energy level, if you will. And that's the distribution of where you can find that electron. And then you have the second level, n equals 2, if you will, where you see the electron, and that area is sparser because the electron is less apt to be there. And on this particular case, it's a bit different because this could be an electron that is being excited and then dropping back down again, and so forth, depending on how they actually have made the image and whether this material has to be stimulated to do so. So it's quite interesting. But what you can see is that, and if you do look in that inner one where there's the colors are subtle, but you can see it is not uniform, and that the electron is not uniformly available in all the places. It's a little hard to perceive it, but it is true. So if we look at my comments from the Bohr video, here's a graph taken from research. The bottom is the distance from the nucleus, and the y-axis is the probability of where you'll find the electron. So you can see that it is not a line, it is a zone, and that can be shown to some extent what I've been saying. If you look at this graph, we've now added a couple of energy levels. The 1s plot is really the same plot we saw in the previous graph. Now we've added the n equals 2 and n equals 3 levels. Now notice that the probability as a function of distance for the 2 and the 3, the amplitude is less. But let's also look at how wide the base of those happen to be. And we just do a rough estimate here and see, just to give a sense of the area under the triangle, under the graph, if it's similar. So at least theoretically, the area under each of the different color curves has to equal 1, because the probability of finding the electron in that area is 100%. It can't be anywhere else if it has that energy. What I want to show here is that in the previous diagram you saw the dense, aside from the nucleus, you saw this dense area that was pretty uniform. And you can see by the peak of the purple line, the 1s line, that there's a fairly narrow zone of where that can work. And then we see the 2s curve. Now what you see there, in my guess, is it's sparser. And the distribution, of course, has a longer way to go around. Now what's hard to tell here is whether the electron is excited and whether or not that's completely mapped or not. That's a fairly difficult question, and it's hard to say if there's been any effort in the 3s level. So, you know, that's whatever. But it just shows that the location of these electrons within these orbitals is not fixed, and that there's a way to look at that in a non-calculus way, as I've suggested earlier. So when we have an atom that has more than one electron, the inner electrons are creating a screening effect. You can see here in this particular diagram, the blue area are the electrons external to the electron of interest. And due to the Shell theorems of electromagnetism, they don't affect the inner electrons. But the electrons inside of that, the ones in the green zone, certainly do. And so this also will affect how much of the nucleus that you can actually perceive. And there's different ways to model this. But given all the different possible ways electrons can be moving around the nucleus, and the fact that that can change quite easily with stimuli, makes this quite a difficult thing to model. So here we have the orbitals of the n equals 2 energy level. You have the spherical s orbital, and you have the 3 p orbitals, the dumbbell-shaped orbitals that we often get to know. And the question that I'm suggesting here is how well do we really know this? Well, I think probably at this level it's pretty close. The challenge is that when we look at, say, carbon or one of these atoms in that area there, and halogens, we know a fair bit about them, and we've done a lot of spectra on these atoms and so on. And so everything there's been a lot of research. But the problem is that when you add all these electrons to the atom, and you have more than one, you have many of them all in different orbitals and circumstances, this will distort because the electrons will act on each other, and they will also be acted on by the nucleus. So there will be a complexity going on in all of this. In addition to all that, you have quantization effects, quantum world effects. This is not a planetary system, as I said earlier, and it's not a planar system, as you even can see in this diagram. It is a three-dimensional system. There's a lot of things going on here. Now remember that the dumbbell shape that you see there is a probability zone of where the electron can be found at this particular energy and circumstance, whatever that means. The other thing that you need to know is that even with this model, If you go to the next level, so we go, say, down another level to, say, silicon, you're going to see that the next level, the n equals 3 p orbitals, although they're dumbbell-ish, do not look like these ones. And so, again, there's a simplification that is given. And I'm not saying for the minute that young people should be memorizing all this stuff. I don't think that's fair. But I think we should make them aware of it so that they recognize that, the world is certainly more complicated than they might think it is. So let's sum up a little bit now as we've had a look at some things. So first, think of Bohr's orbits as energy levels, not pathways. We really want to get away from the solar system idea because it isn't valid. Remember, we're dealing with a quantum universe here, a microscopic world that operates at a different situation than it does in our macroscopic world. We're seeing the average. In the quantum world, we're seeing this unique effect that we don't see day to day. So we have to be very careful about the metaphors we use to model it. Understand for sure that the carousel model that is typical in high school textbooks, where the electrons are arranged in a kind of a merry-go-round type shape around the nucleus. This is abject false. This is not true. Electrons never do this. They don't behave this way. And I don't think it should be in the books. I think it should go. Remember that electron paths are not in a single plane. So even when we do Bohr's atom, we have to remember to some extent that that's also something we have to think about there too, because again, all we're talking about is energy levels. We're not talking about where the electron really is. I mean, we can sort of divine that if we're dealing with circles. But no one's saying the circles all have to be in the same plane. And so we have to be careful, again, how much we take that with us too. So even if we're dealing with the Bohr atom and the energy levels in a more responsible way, we still have to think of this in 3D. And a lot of times we don't bother modeling it in 3D because that of course makes everything more complicated for people first learning the ideas. So 3 more points as we end this. So the screening effect, when we add more than one electron around an atom, is going to affect the paths of all electrons. As electrons change energy levels, it's going to affect the paths of the other electrons. And this is complicated. And so that's fine, but let's understand then how much that we should be cautious about what we think we know about how these things work. Number 5, the orbital shapes are further complicated at higher energy levels. So I said already that the orbital shapes may be affected anyway. But regardless of that, the p orbitals at n equals 2 are different than the p orbitals at n equals 3 and beyond. So they're not all the same, and that's something else that changes. And that's true even if we have only one electron. We can go forward and model it that way. The last thing I want to mention is the electron density plots, and showing that the electron is not in a specific orbit, but is actually in a zone. And even though I gave you this ellipsoidal way to look at it so that we don't have to get into difficult mathematics, but it does try to convince you that the electron cannot follow a given path. There's a lot of reasons why, and is not simply following a single orbit. So if nothing else, let's please dispense with the planetary model, which is completely invalid for this. And second, let's dispense with the carousel idea, which is patently false about how electrons behave around the nucleus. So hopefully, as you continue in your study of quantum mechanics, part of my work here is trying not to have you go ahead with some of the more silly notions that have unfortunately been around in the past.
So here's an example of where I think Bohr's work gets misused, and I just wanted to be blunt about that so that you can see my thinking and you can decide if you agree or not.